Okay, I think we're going to start out the planning session by giving Greg Anderson from NSF an opportunity to say a few words. So, Greg?
Thanks very much for the opportunity. So I just was going to try to say a couple of bits of news and a few other things that I'm intending to hopefully help kind of encourage people to think for this planning forum and what you guys can do with the time that you have remaining together and into the future. So we'll try this again. Thanks for the opportunity to talk. Really, my goal here is to give you some quick information about some things that are coming up, administratively and things like that, solicitations and such. But then also to give a little bit of thought that is intended to help spark the discussion through the planning forum today and into the future about kind of what's coming up in 2018, what does this mean. So I wanted to start off, though, by taking the opportunity to say congratulations. David's not in here right now, I don't think, because he's sporting the MATLAB shirt, and that is really bright. Oh, there you are, David. Okay, well, it's really bright. It's obvious to find you. Congratulations and thank you. And I just want to say, at the time that I have this opportunity, that I've enjoyed working with you these past 5 years, and I wish you all the best. And I want to congratulate Bob for taking on this new role, and it's going to be an interesting thing working together in a different capacity. But I also wanted to congratulate Iris and the community as a whole of 30 years of a dynamic and engaged community that continues to be dynamic and engaged. And this morning's talks were some pretty cool things, I thought. I was intrigued to see the spread of that. So, some simple things coming up. There are 2 solicitations out that you probably want to know about. Maggie and I spent some time putting together a new ERSCOPE National Office solicitation. That's out there. The solicitation deadline is September 26th. I encourage you to look at that solicitation if you're interested. Talk to Maggie. Talk to Ramon Arrowsmith. Ramon's also, the current National Office team has put up on the website information that may be interesting to you if you're going to think about putting in a proposal. But take a look at that one. And the other one is that there is a new ERSCOPE Science solicitation out, and I've had some feedback from the meeting that people are definitely planning to put things in, but weren't aware that the solicitation has been revised. The solicitation has been revised. You need to read it. It does have some significant changes, and in particular, it has some changes about information that we want to see in there that previously hasn't been a requirement, but increasingly has been a strategy that the most competitive proposals have used, and we've added those as a requirement so that everybody knows that this is a useful piece of information. The other thing is it has, as was discussed yesterday at the breakout on Pascal, a requirement now that if you are going to make use of portable instrumentation through SAGE, you need to get from IRIS what's called a letter of support commitment that describes to you as the PI and to us as POs what support IRIS can give you if your experiment is funded. So talk to Bob Woodward, I think, is probably the best person to go after for the moment. About what these letters of support commitment are, and please, to make things sane for folks at IRIS, don't wait till the last minute. Bob.
Just a point on that, there's going to be a bulk mail message that's going to come out probably next week that's going to provide information on this requirement.
Okay. So to relay, in case folks couldn't hear, Bob was saying there's going to be a bulk mail message that talks about the letters of support commitment and how to get one and that sort of thing. I would just encourage you to try not to wait to the last minute on that, because then they'd have a big burst of things to deal with. So transitioning from kind of the quick business that has to be dealt with on this sort of a thing, I want to talk a little bit about the future and give you some encouragement and some thoughts to chew on. The first one is ERSCOPE in the post-2018 era. Okay, what does that mean? ERSCOPE was designed as a 15-year program, started in 2003. There's no guarantee that any specific current element of the ERSCOPE program will exist as it does today after 2018. But the data won't go away. The ERSCOPE facility components, the PBO and USRA, have been integrated with the core facilities together under GAGE and SAGE. And the recompetition in 2018 is really about sort of what's going to happen next with the facilities that we're talking about. So the high-value components that exist today as Stereoscope facility may well continue to exist after the competition. It's just that I can't tell you today which ones or any specific ones that we would do that. So that's that. Other comments, people have been talking a lot here about sort of what is, the phrase that gets used is the next big thing. And I actually myself don't really like that phrase very much because it has some specific implications. So first thing I'll just say, I agree with Jim's comments earlier this week. It's probably too late to do something that is on the scale of an MRAFC experiment. In GEO now, that's $130 million. It's probably too big for that before 2018. And moreover, the community may not actually want a single next big thing, whatever that is. There may be multiple medium-scale things that are the way that the community thinks we ought to go forward. Other communities may also have their own things that they want. And so it is a gap, and NSF knows it's a gap, and we've talked about it internally a lot. It's something we have to address to try to figure out what to do about that. But again, that's another thing that takes enough time that it's going to be something we probably don't have a good solution for in time for a single next big thing in 2018. So this is really, the 2018 competition that we're talking about really isn't about the next big thing, whatever that is. It's really about capabilities for the future. So again, to give the timeline, because this helps for folks, 2018 we have to have some new awards for a set of capacities to do something that is the science that folks want to do. That means that in 2017 the proposals have to come in and be reviewed and go forward to the National Science Board, assuming that we're going to go forward. Which means that in 2015 and 2016 the solicitation has to be developed and out the door and put on the street for folks to be able to respond to it. So the big question that's out there right now is, what should that solicitation look like? What should it have in it? How should the structure be? And we don't know inside NSF the answers to that question, and we need your help for that, okay? So we want the community input to help define that. And Bob made some good points on this particular topic that I want to riff on a bit. We need to talk about capabilities. But first, you need to talk about the science. What is the science of the 2020s that the community wants to do? What are the capabilities you need to do that? Okay? Think in that order. You may, just because of budget realities, have to give up some capabilities that you have today in order to get what you need for 2020 and 2025 and what you want for the future. You may have to make a trade-off. But that's okay, because science evolves, and so do the community needs, and so should the capabilities. Also, this morning's talks were a lot of very interesting frontier discussions, and it's useful to think about the fact that this is an opportunity to go after other avenues of support and partnerships to make some of those things possible. So that's something else to consider. So my final encouragement to you is this. Something is going to exist after 2018 in a different form than it does today. We don't know what those somethings are, okay? But there's going to be something different. That's going to be defined through an open, fair competition. That's the commitment we made to the National Science Board and to the communities. And that's a commitment we're going to uphold. But we don't know what the form of that is, that competition yet, and we need your help to help define it. We need your input on that. So please get involved. Please make your voices heard here and at other opportunities that will be coming out in the next year, I suspect. Make sure that you say what you think folks need to hear, and make sure your voice individually and as a group is heard. So that's my encouragement to you. And I will take questions if folks want, or else I'll get out of the way if folks just want to start talking. Okay. Thanks.
Well, the next part of this planning forum here is we're going to hear from some of the people that led some of the SIG, the SIGs during the course of the meeting, and perhaps from some of the thematic Grand Challenge groups. And so we sort of asked them to come and give a brief summary with particular focus on some of the issues that Greg mentioned in terms of future scientific opportunities and the kind of facility capabilities that are needed to address those scientific opportunities. So I think we're going to start out with John Hull.
Yep. So, what do you do here? Oh, we put everything on your computer, don't we?
Yeah, it's there's a little older. Okay.
Back on. Get on my first slide. Just a sec. That works? That works. So I was asked to report on the large N SIG, as well as which was Monday, and then on Tuesday a SIG that talked about iris interactions with industry. I wanted to also define a little bit what is wave fields versus what is large N. I've heard it said several times, not quite right this week, so I did want to clarify what those are. And actually, I really like what Greg said because I think I'm going to target what I'm saying in a very similar way. HiNet is great, but HiNet is great for the same reason that USA Array is great or the Long Beach Dataset are great. They're great for the exact same reason. And they're great because they're large aperture, densely sampled, continuously recorded arrays that are capable of recording wave fields. And when we record wave fields at the tens of seconds scale or at the tens of hertz scale, we're capable of doing things that we simply cannot do when our stations are very long distances apart. It's not to say we can't get very useful information from systems large distances apart, but we could do new things. We're enabling new science when our systems are close together. So you're all very aware of these two data sets, one of the tens of seconds scales, the other the tens of hertz scales, where we truly are recording wave fields, not just wave forms. Wave fields are useful because these densely sampled large aperture arrays, ideally continuously sampled to get all sorts of records that we didn't anticipate, enable a whole series of methods, wave field imaging methods, that are different from the traditional single station, and you have an array of single stations that you then do a non-unique inversion. In this case, you're directly imaging with whatever your favorite method is there. If yours is missing, tell me, we'll add it to the list. And this imaging directly tells you what's going on down there, and it enables these methods don't work with sparsely sampled stations, and they enable us to get higher resolution images of sources, higher resolution images of Earth structure, and therefore they enable us to see things that we simply couldn't see before. And in many cases, we have no idea what we're going to see with these things. We don't quite know till we've gone in there and looked, but we're seeing new things. So this technology of recording full wave fields is enabling new science. The Recording the Full Seismic Wave Field Workshop series, that those of you paying attention to the IRIS listserv may have seen, is about enunciating what we could do with full wave fields. So please look up the IRIS wave fields website. You can see it listed there, or just Google IRIS and wave fields. And the goal of this series of workshops is to answer the question at the bottom, what new science could you do if you had, at whatever your favorite scale is, full seismic wave fields? And the goal here is to enunciate that scientific benefit at all scales, from global to soils. And if you think of a different scale we haven't thought about, please tell us. What could you do? So I'm actually a little bit disappointed that the wave fields big at large N SIG was at the same time as the global arrays, because quite frankly, global arrays is this as well. We don't just want to enunciate it. Our point is to gather that information such that we can enunciate it and promote it. So we're going to gather materials at all scales, from global to the environmental scale, and produce the appropriate documents that we can then start talking to the funding agencies in an intelligent way. But the point here is the science. Quick example from my own work, very, very quickly. I'm just going to say we put enough stations down on the ground after the Virginia earthquake that we're back projecting earthquakes, much like Ishii and others were doing with global earthquakes, but we're back projecting aftershocks in this case. And the bottom left corner is a back projection image of a magnitude -2 earthquake. And the right-hand panel, and I'm not going to go into it, we're actually watching rupture propagate through three-dimensional space and time on magnitude 2.5 to 3.5 earthquakes. Orders of magnitude smaller than what we can do when we're limited to wave fields at the seconds to tens of seconds scale. We're now looking at tens of hertz scale. So I would argue that wave fields have been transformative for our science over the last decade. The two wonderful iconic examples, HiNet being another wonderful iconic example, that we're doing it. We're doing it at the tens of seconds. We're doing it at the tens of hertz. In both cases, I think we can learn a lot more and do it a lot better, so we should absolutely continue to invest in this, absolutely. But between those scales, between approximately 10 seconds and about 10 hertz, we can't do it. We don't know how to put enough instruments on the ground at these periods to actually record full wave fields. We don't know how to do it. Industry doesn't know how to do it. So there's a gap here. And it turns out that gap has a lot of applications of huge societal relevance. There's a list right there: earthquakes, volcanoes, nuclear discrimination, induced seismicity, energy resources, the oil industry, thermomechanical processes, internal dynamics, and fluids in the crust and lithosphere. I'd like to make sure that that's on our table as an IRIS science target. But we don't know how to put full wave fields on the ground, record full wave fields at this bandwidth. And you'll notice that this bandwidth doesn't just have one funding agency. This bandwidth has multiple government agencies as well as industry that is very interested in problems at these scales. So it's not just one source of funds. Which brings us to what is large N. Large N is a subset of wave fields. Array of arrays at the global scale is another subset of wave fields. Large N is the goal to close that gap, to be able to enable us to deploy orders of magnitude, 1 to 2 orders of magnitude, more instruments per deployment, with instruments that are high quality at the bandwidth of 10 seconds to 10 hertz and beyond. These instruments need to be different from the ones we have today, or the ones industry has today, much less expensive, simpler to deploy, simpler to get the data out of, large data volumes, that becomes even more important. But we must maintain high quality signals, that's why that's in yellow. And of course, we'd love it to be more robust. So large N on a volcano might be 5 as opposed to the one they can afford today. It might be a small number, but it's going to be something new that we couldn't do before because the instruments are better. So our goal here with large N is to do this, particularly targeting the 10 second and 10 hertz bandwidth and beyond. And the good news is the technology exists. It has not been packaged in a single package, but all the parts for that technology exist today. It doesn't exist in a single package because nobody's asked for it. It doesn't hit the traditional instruments that we've been requesting in the past, but the technology does exist in order to deploy thousands of sensors at the 10 second to 100 hertz bandwidth. And I think we should be pursuing this. This is an enabling technology. It will enable us to see stuff we could never see before. That's new science. So, just to reiterate, wave fields is the idea that density sample arrays with large apertures allow us to enable new science. Large N is a subset of that. It's an enabling technology to fill a gap on wave fields that we can't do today. That's not to say we should abandon the other scales, but that's to say that we should add a facility to do another scale. I was also asked to talk about the interaction between industry and IRIS. And somebody at that meeting started off the conversation by saying IRIS might be analogous to an academic organization in computational science that never talked to Silicon Valley. I think there's a certain truth to this. We need to talk to them a little bit more often. The good news is we started that conversation. There's 3 workshops I wanted to point out here. There's one, a luncheon meeting at the SEG meeting. For those of you who've never attended SEG, the SEG meeting is about 25,000 people. It's analogous in size to AGU. They're all exploration geophysicists, and of course, 90% of them are seismologists. Okay? 20,000 plus seismologists in a room. We had a luncheon meeting co-sponsored by IRIS, Caltech, and some oil companies, some energy companies. We had another meeting last week in Houston, and we had, again, co-sponsored by IRIS and technology company, industry companies. And this, completely independent of this, there's an SEG-AGU collaborations committee that has fostered a workshop next month in Vancouver. And all 3 of these workshops have 75 to 125 people came, 2/3 of whom were industry, who were extremely enthusiastic about this concept of talking to each other, and the other third being us. And they were very successful in actually building bridges across this gap. What do we have in common? I'm going to focus on the first 2 because those are really the scientific goals that industry is interested in, that we have a lot of expertise in: full wave field imaging. They're interested in getting more, as the first talk this morning talked about, out of the data set. And the other one is nanoseismicity, the hydrofracking situation, understanding fracture mechanics. And the next 3 on that list are really enabling industry to look at those first 2. Dense broadband instrumentation is something that they haven't quite solved that puzzle yet, nor have we, but we could work together. That's large N, to be honest. Passive imaging and ambient noise interferometry, something they're picking up and getting more and more excited about. 3 components, something they've been working on for decades, but still haven't figured out. The next category, data standards, large data volumes, and HPC, is something that they're orders of magnitude better than us at, but they're still struggling with, they're still working on, and absolutely we should be part of those conversations. And finally, data sets, both data sharing of their existing data sets, of which value we can get a lot of value out of, but also jointly acquiring data sets. And I wanted to highlight just last month, IRIS, Nanometrics, and Nodal Seismic co-deployed on an industry shoot. This is an industry fiber-size 3D grid, deployed both broadband, our Nanometrics broadband seismometers, the ones that went up to hundreds of seconds, and thousands of industry Zealand nodes that are set on continuous recording, like the Long Beach array. And this is going to be an open data set that's going to be shared by the oil companies and by us. This is going to be at the IRIS Data Management Center. All sorts of opportunities here. But the other common interest, let's be quite blunt, isn't our expertise. Industry wants our expertise. They will invest the resources, and they will catch up, and they will pass us. But the one product that we will always have, that they will always want, is students, the workforce. So I think one of our sales pitches when we talk to IRIS should be that enabling IRIS seismology, both education and research, improves the human resources pipeline, not just at 1 or 2 or 5 universities, but at 150-odd universities. And this is something that the human resources departments really don't know about, but could learn about. And several ideas at the bottom, I'm not going to go into those, have been mentioned, but we need to start thinking about how we can better interact on the education outreach side of things. And finally, I was just going to say that workshop, SIG yesterday, ended up by saying, what do we do next? Is it consortium? Who are the champions going to be? Are we going to develop a working group? Should we talk about an industry consortium with IRIS? And please forward your ideas to Emily and Bob and anybody else on the board. I'm sure would be welcome to hearing about this.
Yeah, let's see. Any questions for John?
Or comments?
Comments? Okay, thanks. Thanks, John. So the next presentation is going to be on seismology in the oceans by who's?
So my marching orders were 3 slides, so I'm not going to be large N.
I didn't read my marching orders.
And it's 3 slides on 2 SIGs, one on extending our presence in the oceans, and the other one on real-time seismology in the oceans. And this first slide actually shows the different options. We have, of course, the classical OBSs. One of the things that we are seeing is now, if they're close enough to land, we can have a direct link. John Orcutt even reported on a project to connect northern Canada with Norway with a cable and put all kinds of instruments on there, not only seismology, but also acoustic sounders to measure the temperature changes in the ocean. But the real interesting things are now have to do with the original mission of IRIS, and that is to cover the Earth with seismographs, the Global Seismic Network and the Pascal missions. So for the Global Seismic Network, 2/3 of the Earth was really ignored, more or less. We had a few island stations, but it was a big gap. And that may actually now be filled with what we call the wave glider. The wave glider is a robot that floats at the surface of the ocean, and that's able to make an acoustic link with the OBS at the bottom. The OBS might actually be disposable. In this way, you do away with the very expensive ship costs, and you get your data in almost real time. This development has just started. The first results are coming in. They are still in the process of solving some of the technical difficulties. There are, of course, tethered hydrophones that could also be collected. The data of those could also be collected by the wave glider. Another development is these floating seismographs, the mermaids. They seem to work now. We get data under good weather conditions, even under magnitude 6. We get good seismograms. Under more realistic weather conditions in an ocean like the Indian Ocean, it's more like 6.5. But teleseismic data are seen on these mermaids. local events, we can go down to magnitude in the 2 to 3 range. The shortcoming of the mermaids is all you can see is the P waves, and you don't see an S wave. And the same is true for hydrophones tethered on a buoy. This is an experiment that Frederick Siemens is trying to do. So there are all these new capabilities on the surface, and we discussed them in these two SIGs. The basic conclusion is the top line. The oceans are about to be opened up, and this is a major step forward. It's going to be transforming for seismic tomography, both on the global scale and in local experiments. We can have the kind of density in local experiments that US Array has. These mermaids are floating, so they move actually at the speed of US Array. And so we are doing a wave field imaging in this case. The mermaids, the next generation of mermaids will be able to communicate to each other, so you can also use them in a rapid response capacity. So that's going to change the science. There is a trade-off there between quality and quantity. An OBS at the bottom can record the S waves, can record the surface waves, so you get a complete seismogram. However, the OBS is fixed. It doesn't move like a mermaid, and it's more expensive actually to get the data out of it. The cable, the OBS, either cabled or not, will always be needed in addition to these floating seismographs. But the floating sensors are needed to give us the full wave field, and that's the message I think that I picked up from many other SIGs in this workshop. A few other remarks. First of all, ocean experiments always cost much more than land campaigns. And when land seismologists, like most of the IRIS people, are actually going into the oceans, I think NSF should be aware that the separations between EAR and OCE need to be broken down, and that more and more seismologists will do ocean sciences type of experiments. OPSIP has attracted many new OBS or users of OBSs or of the OBS data. But one of the things that we observed is that not everyone is aware of the complexities of OBS data, and it would be nice to have some educational component to OPSIP, either a workshop or webinars or that deal with the practicalities of using OBS data. Differential pressure gauges help increase the signal-to-noise ratio of the OBSs. And last but not least, if we are doing these ocean observatories, we have to go multidisciplinary. There are many people who want to do measurements in the oceans, and it is a waste of money and not to use the instrumentation that we have if we can just hook up a simple thermometer on the mermaid helps the oceanographer, for example. We can do high-frequency acoustics. It helps the biologists. All the talks this morning had to do with multidisciplinary. And one of the things that I noticed and that came up also in the SIG is how difficult it is to do things multidisciplinary. You can go out to a meteorologist, or you can go out to a geologist, or you can go out to a biologist and say, I'm doing this, would you like to join? And often you get just a shrug of the shoulders because everybody's busy with his own projects, and it's very difficult to actually get people together and use the synergy. And there I think there's also a message to NSF that what can NSF do to stimulate these kind of multidisciplinary projects. That's, in a nutshell, these two SIGs that we had this morning, or yesterday.
Any questions for who's? What do you see as the next steps in the evolution of this?
So one of the things that we still don't know is how valuable the floating seismometers are going to be versus the wave glide or the increased presence in the ocean. This trade-off between quality and quality, we have to get some experience with the floating seismometers to see how well they do, but it's clear that they work. That's
My other question was, what's the bandwidth limitations of the wave glider acoustic link?
And,
that
you know,
I
how
need
does-
to,
how does that affect the
that number was somewhere, but I must confess I forgot what it is. Is there anybody from Scripps here who can answer that question?
John? The band, the bandwidth limitations of the wave glider acoustic link, for an OBS.
It's primarily a battery issue, and the system we have designed and built is designed to return data 1 sample per second on 4 channels, a vertical, 2 horizontals. This is continuously, and the DPG, the higher frequency stuff, 40 hertz and below, remains on the package, and if the package is recovered, then the broadband data can be returned. But like all these things, you can request that the system send back segments of high frequency data for interesting events. You just have to watch those battery discharges as time goes on. But the idea would be able to do it for 2-year deployments. It could be longer, but the goal was, in terms of cost, that it would be comparable to the cost of operating a GSN station on land over the same period of time. So that was the goal, and probably achievable.
Great, thank you. Any other questions? Yes, Victor.
I was just reading about a transatlantic cable that they're going to put down to save about 6 milliseconds of time across the Atlantic for only about $300 million. Is there any possibility to piggyback on top of something like that? Say, pay an extra $5 million to...
I'm probably not the one to answer that, but the Hawaii 2.0 experiment was not really too encouraging to do this. We spent a lot of money putting a seismometer there that was cabled on a piggybacked, essentially, although that was an abandoned cable, and it was not a very big success. Anybody from the GSN who might wish to contradict that? Okay.
Okay, thanks, Louis. So the next presentation is going to be on high-performance computing and Earth models. And Carl,
All right, I'm summarizing 2 of the SIGs, one on HPC and one led by Rick Astor on velocity models. They are connected, and we've had sort of there are different states of discussion, as you'll see here. So the first point is that for the HPC SIG, especially for those of you with your browsers open right now, you can go to the CIG webpage here, and there's a PDF, and this represents a lot of work of a few people trying to organize our thoughts. So I think this is going to be a valuable document. It was released on Sunday, and I really encourage you to download the PDF. There's the 2-page executive summary, and if you want more, please read more. It's a pretty extensive document to outline the needs, a lot of which have come up here at this meeting. And just off the top of my head, what those needs might be, we talk a lot about big data acquisition, and we'll see that big data needs big processing. And once you stitch that, for example, to the things that John Hull was talking about, the imaging side, we really need the high-performance computing both to handle the data and to handle some of the problems we're interested in. And those might range from uncertainty quantification to just simulation with higher order techniques, or just general exploration of model space. We all have needs that could be made easier, and we're trying to eliminate some of the barriers to these resources. And that's the outline here. So here's the title, Advancing Solid Earth System Science Through High Performance Computing. These the authors in alphabetical order here, Lorraine Huang from CIG, Tom Jordan, Luis Kellogg, Jeroen Tromp, and Ray Willeman have led this effort. And this is, as you see from the logos there, CIG coming from, you could look at the software side, Iris coming from the data side, Lawrence Livermore coming from a very promising partner side, and I would say resources side in the sense of running what I think is the largest or fastest computer in the world, or very large, we'll just leave it at that. And then SCEC representing kind of a all interest in the sense of integration of data resources and software to answer specifically earthquake problem, whereas CIG covers geodynamics and more broader scales of earth sciences. So we'll watch this animation. This is actually a pretty good metaphor, or another word for a pictorial representation of the issue here. The pyramid represents sort of HPC capability and capacity. The goal here at the bottom is that we're all occupying with our desktops, perhaps small clusters. Maybe your Mac has, 16 or 32 cores or something. We're working on, we can do a lot of science. We're efficient. We can tackle a lot of science and development at that scale. The latter is to say that some problems, specifically science problems, and many questions that have come up here, or even if you look at the desire in the 10-year EarthScope plan to tackle physical systems and integration, those are complicated physical systems that need computers that hold a lot of memory. So this mesoscale computing, the first step is to try to bring as many of us for problems we want to work on toward this next level, and there are major barriers. So the latter represents how do we get toward access to the next scale. We may not have a cluster, but we want access. We need expertise to help certain challenges there. And then the next scale is to say in some generation where there are several people in the community maybe answering certain questions, there remain questions that can only be answered at the really uppermost scale, where, for example, in the global seismic wave field simulated at 1 second. That runs on several 100,000 cores. If there are science questions at these scales that are really can only be answered, we want to at least provide that pathway as well. But I think from my perspective, the real exciting part is trying to get through more people in at the bottom and looking toward this middle tier of answering a lot of different science questions that we want to enable. So that's the sort of context, and the white paper outlines sort of what in the context of what is available right now, both at this sort of we heard Gary Pavlis talk about this, we're all at our workflows, individual research groups, and then we're really looking toward, and then you may have something like XSeed that's out there but not actually functioning that well for our community and the certain kinds of workflows and data-intensive problems that we have. So this comes out of what's existing now and why we need something more or something different to start thinking about. So I'll just read them. NSF programs to sustain deep collaborations among solid earth scientists, and computational scientists focus on extreme scale computing in solid earth system science. We need coherent processes for allocation of HPC cycles. This is kind of arising from, at a certain scale, the challenge of, you may submit for a science question to one program, but you need to submit to get the resources from another. You're going to run this on a machine that you might not be familiar with or know anyone who's going to really have the same vested interest that you have in trying to succeed with the science. Support for software engineering teams dedicated to solving extreme scale problems in solid earth system science. So the fact is we need this core human people, say a group of 8 or so, that can understand the workflows and help guide you toward your science goals. That's really a key component of this. Dedicated allocations of computers with sufficient memory and data storage, so just the right resources to doing the science. accommodating large amounts of computing and also enabling the step up for certain science problems. And then the last one is strategic alliances between NSF, DOE, and other agencies. So these are some of the bullets that came out that are in the white paper, and there are a lot of science examples that start that whole motivation. And I think, as we've heard here, this is driven by science, not just the need for we want bigger data sets or we want bigger computers. We are driven by certain science questions here. So I wanted to add there was a really nice group of Lawrence Livermore National Lab folks that came here. They have a strong seismology group. They have resources that are being developed specifically for problems that they're interested to and also that we're all interested in. And one example here that's not really hit in the white paper, this is a slide adapted from Stan Rupert, is just that, for example, this was news to me anyhow, that traditional HPC is not really effective or made for big data HPC. So there are the idea that there's different infrastructure for handling. In this example, they had 300 million seismograms and they wanted to cross-correlate them. You know, that's not, we're not going to pull that off on small clusters. And, you know, I'm sure a lot of people would be interested in here if they given those kind of opportunities. But the point is that just in the infancy of developing these different big data HPCs that are driven, I guess, Google, Yahoo, some of these companies, they had a 19 times speed up for a tenth of the cost, and probably these things get better and better. But the point is that actually the data, at least the Livermore point here, was that the data and the HPC towards simulation are actually not the same machinery, but across disciplines where data is needed, this is something to think about. And so that was a point there that's not hidden hardly in the white paper itself, but we should think about. And so finally, who knows that the IRIS DMC is mirrored at Livermore? Raise your hand. Lots. That's great. So maybe for the rest of you, the IRIS DMC is mirrored at Livermore, and that's an example of that when we want to do science or processing, certain things are going to be way faster having that connection, and that's an example that's functioning and promising towards the kind of partnerships that we're looking for. And so please check out the white paper. Moving on to the velocity model. Rick Astor led, and by comparison, I think this is a topic that's probably been around, sort of representation of velocity models, characterization of uncertainties for a long, long time. I'm sure longer than I've even been alive. But this topic should come up repeatedly because, I mean, in my mind, this is a grand challenge. This is a question that's been open forever, and you know, it may not. When we want to characterize certain things about the Earth structure at some level, you know, uncertainty of the kinds of results we're producing will give us information of the people using those models and, you know, really a little more legitimacy within the scientific community of representing our results. So Rick's initial bullet points were a lot more coherent than the notes that I took, so I thought I'd start by showing the charge and just where this was going. So this is looking at possible topics, tools for more completely investigating resolution, examination of regularization, biasing methodologies, dissemination of models, expectations for peer-reviewed manuscripts presenting or utilizing velocity models, the idea that through peer review we can actually steer some of these things, issues related to interpretation in terms of temperature, attenuation, phase, it's mineralogical, etc., improving sharing of models, model-based collaboration with other communities. So those are the initial points that we hit. Some of these, I'll just, I think one of the themes that came circling back was the IRIS Earth model collaboration. So as an example of start somewhere, put something in a place where people can at least download, make cross-sections, and I think it's a really valuable standard that can be promoted through whether it's, you know, a data management plan or a reviewer, but we can start to, or just serving as a good example, put your stuff out there and let it be at least visualized, and then that could be a step toward what the question of saying what more information, for example, uncertainties, resolution tests, we have to build what those quantities are to better characterize the information that we have. So Earth model collaboration, please, there's a lot of you in this room who've used it, but we just want to promote that. It seemed to be the one thing that is a stepping point to doing something more. And this is a snapshot Rick took from just what kind of information was there. I think it was to acknowledge, I think it was a Brandon Schmant and Humphrey's model here. But something that really is useful for both, to me there's two threads. There's sort of science, a seismologist wants to know a lot about your model, what the data are, what the resolution is, do we believe this, that, how can we reproduce this, and someone else might want to know very little about your model. Just give me a slice and maybe how much do you believe these information. So we do have different objectives in delivering information, but certainly delivering more, you can always take less from that. And so I sketched out a few topics just from the notes of people talking. Scientific reproducibility is, a huge challenge in terms of, we can extract the data, the workflow to actually run the codes. This is, seemingly impossible in our community, but are really something we should think about, the reproducibility. Desire to have intermediate data products. So even though we start with waveforms in many of these formal inversions, we're distilling that into some other quantity. That's something that might be deliverable or something that would go with these models. How do we promote the EMC and manuscripts and proposals, making it more of a standard? I put Jeroen Ritsema just some positive examples of putting more information. He said he puts his models, he puts his data, you can run resolution tests. That's a great standard, and as he acknowledged, that takes a lot of work to put up there, and so maybe there isn't the returns on that we want. But the general theme representing uncertainties, as simulation gets easier, we may have more Monte Carlo realizations, so for smaller parameter problems, this is probably the way to go, something that is enabled. Generate 1 million realizations of your models and then distill that to some statistics. Infrastructure to sort of a pipe dream, picking models, picking earthquakes, and interrogating other models through simulations with independent data. Paths forward, we really, it's not as mission-oriented, I think, as some of the other SIGs, but promoting, I think, the EMC, encouraging the inclusion of an uncertainty and resolution information, and trying to develop some standards. And lastly, there was an issue about, is there a place for dumping accessory information? These electronic supplements get larger and larger. Some journals don't want to see them. They don't want to see your 5 different models. And that's, so thinking about whether IRIS or the EMC would be the place for archiving, like a library, this sort of information was a topic that came up. So that's sort of the state. I'd say there's, as I say, I think of the uncertainty representation of seismic structure being a grand challenge continues. Thanks.
Any questions for Carl? Is Maggie in the audience? Maggie, did you want to say anything more from an NSF perspective about HPC? Why don't you come on up? Yeah. Oh. Okay.
Thank you for the opportunity. And Carl did a great job encapsulating the SIG. I'm screwing this up. I won't touch it any further. Carl did a great job talking about the SIG yesterday and running the SIG, so I want to commend him on his work. So just from the NSF perspective, Eva Zanzurkia has been predominantly working on this, and so I've been working with her on it, and she certainly has a better, very synoptic scale view of HPCA because she has been working on EarthCube, which, as you all know, is still in very much of a development phase. But in terms of high-performance computing, you all have been working on this white paper, and now it's time to think about next steps. And what we see as probably the best way to implement the next steps is something what we consider to be the best way to implement it would be a proposal into geophysics for something called an RCN, which would be a collaborative network proposal. And I wish we could put up that pyramid that Carl put up. Okay. Because this is a fantastic image here that I think encapsulates what we could envision as the network. Am I? The ladders are important.
The ladders are key.
The ladders are key. You're right. Sorry.
Okay. Thank you.
So, and actually, there was a slide above this in the white paper. It's on page 3 of the white paper, which I'm sure you all have in front of you. On page 3 of this white paper that Carl showed, there's 5 identified sort of next steps and requirements for moving the community forward. And those 5 steps, I think, that are really great sort of big picture things that the community needs to focus on. And those 5 key next steps are going to move this community forward, both the everyday computing community, the sort of mesoscale mid-range community, as well as the leadership class community. And what we consider to be this is the geophysics community, and this RCN that we chatted about yesterday in the SIG would certainly focus on the geophysics community, but we want you to consider people outside of just the geophysics community. We want you to think about who else, right? Take a step backwards and think about about the EAR, or the Earth Sciences community as well, because they are not as well poised to articulate their high-performance computing needs as well as you are. And the white paper that you all have created is a great document to use as a model for helping the rest of the EAR community to document and articulate their high-performance computing needs. It's a great model to help them first articulate their science questions, and then ways to help articulate the infrastructure they need to address those questions. And so we're hoping that the RCN will allow them to go about doing this. So as you go about making these, coming up with a proposal for this, that you consider who is in this pyramid, both laterally within the EAR community, but how with who are in these different levels, and then how you get these ladders, or how you create these ladders between these different levels, and what mechanisms you all decide to create in order to create these ladders. And certainly this doesn't have to happen overnight. That this will be an ongoing conversation between you all as a community, IRIS, and NSF. So are there any questions about this? This is very early stages, but again, I do want to commend those of you working hard on this white paper. Thank you for taking the time to do it. The white paper will have life, both within NSF and certainly as something that's going to guide your own community. So thank you for taking the time to put it together.
Thanks very much, Maggie.
Thanks, Bob.
Okay, the final one of the SIG presentations is going to be Keith talking about transnational initiatives, subduction zone observatories, and arrays, and global arrays.
Actually, I just have one, GABBA.
Oh, you just have one, okay.
Close that one. Right, close that one. This one. Oh, okay. So
Okay, so I don't really have any new slides, but what I thought I'd do was just go through what we went through at the SIG briefly. And we did have one sort of new idea that came out of the room, came out of the meeting, and I'll talk about that at the end. Just a little bit of history about this array of arrays. Sometimes it's called GABBA or GABBA. It's been around for, I think, about 5 years, and it came out of one of these group discussions about how to advance the GSN, sort of the next big thing. And there has been one sort of dedicated workshop about this, with this idea of instead of having just a GSN where you have a network of individual sensors, you basically have a network of arrays. And so, the potential of basically building out, each element of the GSN into its own array. So it does have synergy with what John was talking about earlier in terms of sampling the wave field, and so on. And if you wanted to go and see any of the talks, so this was an add-on to the Earthscope meeting that happened in last May in North Carolina, and you can go to this webpage, and all the talks are online. You can see the list of participants, and let's see if I can do this quickly. Okay, it's kind of slow, but I encourage anybody that's interested, you can go and download the talks. There were a lot of perspective talks, people from Australia, people from Germany, people from Japan that had operated arrays for decades, and they had ideas on how to extend things. Not connected. Okay. Okay, and we don't have a white paper, but what we had was sort of one of these meeting reports, and there were sort of 6 outcomes from this workshop. And so we sort of discussed these at the SIG a little bit. This maybe is this mid-range that John was talking about in between, I think it was 0.1 and 10 hertz. So if we have apertures between 1 and 300 kilometers, something of that nature, there aren't really a lot of facilities like that right now. There's all these Air Force arrays that are small aperture. We have the continental scale arrays, sort of like the TA or HiNet, and what they have in Europe, essentially sort of a virtual array. But there's not a lot of these high density, maybe mid aperture is the right way. It's the right way to describe it. And with that kind of an array, we figured there was at least 3 to 4, these grand challenges that maybe we can contribute to. The ones with the green symbols are the ones that I think there's no question that having even just a few of these type of arrays could really generate a lot of benefits. And it's mainly with deep earth. So it's mainly sort of historically what GSN's maybe been associated with, imaging the mantle, doing mantle tomography. With these kind of arrays, you could go to chemical heterogeneity and look for scattering and do scattering tomography instead of the transmission tomography, for instance. I think there's a possibility that these kind of arrays could be useful for sort of tracking microseisms or sources of microseisms. So in terms of understanding changes in storminess, for instance, as the climate changes, there might be a way for this size, because this size of array is going to be really good at sort of 5 to 10 second energy. I think it's still an open question whether you could actually use one of these arrays to do the back projection to study sort of rupture properties of big earthquakes. I think you would need several of these arrays in order to do that and basically combine the beam patterns from all the different arrays. And of course, it's tricky to do that. So we put or at least I put a yellow sort of cautionary symbol about the rupture imaging. Okay, and I went through one example of how one of these arrays could help with deep earth imaging, and this is an example of studying D double prime and basically imaging topography on that discontinuity. And this is work from a recent master's student of Mike Thorne at the University of Utah. And basically the idea was to, as many people have done, divide up the TA into these subarrays. But the problem when you do this is, and there's an example here, is this is sort of the aperture we'd be thinking about, is it's just not very dense. It's a very sparse array. And that's because of the 70 kilometer spacing. And so there are really neat things you can do right now. And this is some of the work that Stephanie did in terms of looking at this SCD, this triplication in the lower mantle, basically making a map of the topography on this D double prime discontinuity, and has this enormous relief. Something like 200 kilometers of relief just over sort of a few hundred kilometers laterally. And this is something you can do with the current technology, but what you can't do with the current technology is sort of take the next step and sort of study the multipathing of this triplicated phase and really look for the 3D structure of some of these features in the lower mantle. So anyway, that's just one example, and these were sort of the issues that we talked about. You know, how would one of these GABBA arrays be different, basically, than just a Pascal experiment? And so some of the things we talked about is that they need to be deployed longer. When you have one of these arrays, it needs to be out for a certain amount of time in order to calibrate it. So you need enough ground truth events, basically, to do the adaptive optics and kind of focus the array. And also, if you're interested in doing something with deep earthquakes, you need to wait several years for enough of these sources to occur to do the imaging. Let's see. So anyway, we talked about this, and there wasn't, to be honest, there wasn't a whole lot of momentum in the room, but we did get one idea, and the idea was sort of what we should focus our efforts on is sort of a prototype version of this, right? So try and pick one place, maybe work together and get a proposal funded as sort of a pilot experiment. And the big idea was that maybe the place to focus on would be in Oklahoma. And the reason for this, there's actually 3 or 4 or 5 different reasons. And of course, one of them is induced seismicity. And there's already sort of an initial backbone of seismometers deployed in Oklahoma because of the really ridiculous increase in seismicity that's happened there. But the other thing is there's deep earth targets in terms of seismicity from South America that's recorded in that part of the continent. There's seismicity from the Western Pacific subduction zones that you could use. And so, for instance, Jeroen Ritsma was in the audience, and he had these ideas, and he knows there's this phase you can get at this distance and so forth. So you could do a lot of interesting deep earth stuff. In my opinion, you could also track hurricanes very well. As hurricanes went up the eastern seaboard of the U.S., if you had an array there sort of in Oklahoma, Texas. And then sort of a fourth thing is there's a lot of weather there, sort of tornadoes, and we heard a little bit about the gravity waves earlier today. And so that if we put out not just the seismometers, of course, but if we put out basically a pressure gauge with each one, then maybe you could do some of these fine-scale studies of gravity waves or some kind of atmospheric dynamics that potentially could complement what meteorologists are already doing. And for instance, like the main severe storm center, I think, is in Norman, Oklahoma. And so there might be other stakeholders, besides NSF. This is something the USGS is very interested in terms of the induced seismicity, and it was one of the top 3 priorities in their budget. And so they actually specifically budgeted for induced seismicity. And who knows, there might be the state of Oklahoma might want to get involved and contribute. And one of the ways to distinguish this from a Pascal experiment would be, of course, all the data would be telemetered in real time, openly available from day one, maintained and curated at the IRIS DMC, and then maybe we could have little contests of different ways that people could use the data that were recorded and see what all the different ideas are that people come up with. And just one other thing, I don't have too much to say about international collaboration. Bob had mentioned that, but at the workshop we had in 2013, we had a huge contingent of folks, and they're still interested in this. And in fact, next summer in Prague, I believe there's an IUGG or IASPI meeting, and I'll be co-organizing a session there with Johannes Schweitzer, who's a longtime array guy from Norway, and he just sent me an email this morning. He said, "What's going on with GABBA?" Okay, so he's definitely interested. I've had email from people in South Africa that they're interested in, which would help quite a bit in improving the coverage in the southern hemisphere. Frank Kruger from Germany, who's operated an array for decades and was one of the original back projectionists, essentially. He's very interested. So anyway, I think there could be a lot of momentum. We don't have a lot of it now, but there is talk of a small subset of us from this SIG maybe putting together the beginning of a white paper or something like that. So anyway, thank you.
I have two things that I'd like to ask. The first one is, please join the Wavefields thing, be part of that document. We are planning on producing a white paper, and I absolutely want the global issues and the oceans issues to be involved in that. And there are going to be workshops, online workshops about that to be part of that document.
Sounds good. Yeah.
The second thing I was going to ask, you mentioned the question of why or how is this different from a longish Pascal experiment. Has anybody tried mining? I mean, at any given date, there are 10 or 20 of these Pascal broadband experiments with apertures of hundreds of kilometers out there on the ground. Has anybody tried mining that data and seeing what array of array type thing you can do with it? And I've not seen those, but please tell me whether they have or not.
You know, the short answer is yes, and the one that's been looked at the most, I believe it was Steve Grand, and it was an experiment that was in New Mexico and Texas, and it was sort of hard to get the data, and a couple people used it, you know, because it was still embargoed at the time when we were trying to do something like this. But there were, I think, Pablo from Caltech and one of his students used that data to do a back projection for a California earthquake. And I don't know that they ever published it, though. But you're right. Those are things to try. And, of course, in my opinion, in general, the Pascal data quality is a little bit lower than some of the observatory quality seismometers, and maybe it's more gappy and so forth. But you're right. I mean, that's a good thing to do and present that at a workshop, and it's another way to look at it. They wouldn't be quite as dense, I don't think. You know, we'd be shooting for like 300 or 400 seismometers. Maybe if there's ones left over after Alaska, then we ship them to Oklahoma, you know, and put them there. So I don't think there's been a Pascal experiment that's been quite that dense. And oh yeah, the other thing is the array geometry, where we might want to have one of these fractal designs so that we span the wave number space as best we can. And a lot of the Pascal array geometries, well, in the old days they were linear. I guess maybe now they're more 2D, but it's unclear how that geometry would work. But it's absolutely worth looking into.
Any other questions? Okay, Jack, did you want to say something about Seduction Zone Observatory?
Apologies for not already being ready to go here.
Pretty straightforward.
Okay. Great. Okay, so this is just a quick off the top of the head report on the SIG yesterday. The Subduction Zone Observatory is a concept that's been steadily gaining momentum for the last few years. It was actually in the SAGE Engage proposals as sort of a potential planning activity for the current time period in both IRIS and UNAVCO. And there have been a number of similar things to yesterday's SIG at various meetings in the last few years. And probably at least a few people in the room were at a really well-attended one at Fall AGU in December. With people literally out the door listening in the hallway. And yesterday's was similarly well attended. And really, as the IRIS board thinks about this, there's really been a very clear demonstration of enthusiasm for this idea. I'm not really going to go through the details of what SCO might be, because I'm trying to sort of keep down to the 3-slide minimum or maximum. But you can sort of read the details here in the next 2 slides. And the general concept, of course, is extremely interdisciplinary and as yet not very specific. And so there's a very wide range of possibilities as to what this could actually mean in practice. But just to kind of summarize, and there's obviously, also a really wide range of projects that are already ongoing that are relevant, if not directly something that we might want to think about formalizing a relationship between a Subduction Zone Observatory and these existing efforts. And so exactly what a subduction zone observatory would be is kind of the big question. And just to kind of summarize my impressions from the SIG yesterday, it was extremely well attended and people didn't stop expressing their opinions sort of nonstop for most of the hour and a half. I don't think I even said more than about 1 slide's worth of stuff. It was really, we had a whole backup of material that we were going to put forward and we didn't use any of it. And I think that very much is similar to what happened at the AGU meeting. And I think the sort of the things that I walked away with is the same as the AGU meeting. The enthusiasm for subduction zone science is loud and clear. The need for this to be a multidisciplinary effort from the beginning is really clear. And the need for international leadership and coordination from the beginning is really clear. And so as we think about what sort of the next steps or maybe next topics to think through, at least for subduction zone observatories, there were sort of 4 categories that were discussed in various ways yesterday. We obviously have to come up with a venue for getting more specific about what science is really high priority and sort of targets that we can build the overall concept around. We have to come up with a mechanism to develop partnerships. This is obviously a idea and project that goes way beyond IRIS. And you could almost, just from the discussions yesterday of all the different things people were talking about coordinating with, you could almost see it as sort of a federation of projects. People were talking about, say, USGS doing things through USAID, whereas we might go through a different mechanism, but all of these things could be coordinated and linked up into a greater whole that really improved data access and open data in subduction zones. I think one thing we as the IRIS community have to think about is defining a sort of tractable and achievable goal that's sort of IRIS's part. You know, this is obviously going to be, if it happens, it'll be a much wider effort than just what IRIS does, but as the IRIS community, we really have to make sure we know what it is we want to emphasize within that bigger effort. And then lastly, I think we have to really think through, a few people made some sort of very telling comments. You know, we need to think through how we make this an effort that really fosters science on a range of scales from individual PIs up to bigger scale, and not just think about hardware, which a lot of the discussions kind of tend to gravitate towards wish lists and hardware relatively quickly, and we need to sort of step back a little bit as we think about exactly what we might want an SCO to be. And so just a little advertisement, there's a bunch of future venues that might have things like yesterday's SIG, and in particular there's one in Bogota that Susan Beck and others are running in about 2 months that will be a really neat way to sort of jumpstart the international part of the effort. And then there's the other ones haven't been organized yet in terms of having an SCO component, but it's probably very likely that there'll be some sort of session at them. And that's all I was going to say.
Well, thank you, everyone, for summarizing the SIGs that way. I think that was very helpful as we move forward with the planning forum as we're going to bring the workshop to a close in not too long. So we're going to hear a few more words. We're going to bring this full cycle around to where we started, back to these grand challenge, the science committees. I think a couple people are here who are going to say a few things, and then Bob and I are going to sort of open up the floor and get comments from you and try to put things that we've heard and talked about together as a group in the last couple days into a framework for moving forward and talk about some next steps, because we sort of have a 12 to 15-month window in which, as a community, we can be providing input to the NSF as they think about what kinds of facilities and science targets are going to be included in a solicitation for SAGE engaged facilities out in 2018. But our window for input is quite short, so we need to be pretty strategic about moving forward. So, John, did you want to say a few things?
Okay, let's see if I can figure out my own computer. Oh, yeah, you want to just grab it? I can, error message isn't going to kill me. Let's see if we have the right one here. It's going to work. Okay, yeah, so, I guess we've heard kind of reviews, and then we've heard reviews of reviews, and I think our goal as members of the Grand Challenge Committee is to look over all these reviews of reviews and see what looks particularly exciting. And my committee has Roland Bergman and me so far. We'll be adding people. So I just picked 4 things that seem like I'd really like to make progress personally and as well as in the field. And there's a list: subduction zones, has rupture work, what's the pattern of strong shaking in volcanoes, and just very quickly, this figure I borrowed from Mark Simon, who borrowed it from Ortega's PhD thesis, and it just points out that in the Tohoku region, there's areas that seem to be locked, there's areas that seem to have a lot of afterslip, there's areas that seem to be continuously slipping, and this is very valuable information. It's both basic science, it's got implications for hazard. It's not unique to Japan. This is a similar figure from New Zealand. The margin there, and it's a lot of detail, but basically you can see the lateral variability in the behavior, and even as you watch it over a decade, you learn it didn't do what you thought it was going to do. And to learn about this, we need to have, I think, ocean bottom instrumentation. I'd love for ours to go in that direction. This is one of the plans Japan's implementing within a few years. Cable on the seafloor with seismometers, pressure sensors. I'm sure they'd like to get geodetic measurements in as well to know ahead of time, before a Tohoku earthquake, just what the behavior is likely to be. I think that's a clear priority for a lot of ways. I then thought this morning we were going to get a picture of what a rupture looks like to kind of motivate the study. And of course, what we'd like to see is how do earthquakes nucleate? Where does the rupture go super shear? We'd like to know how the geometry of the fault, the geology around the fault, the structure within the fault zone, the dynamic stresses from the rupture, what's the pre-existing stresses, and why does it stop? And, there are studies that get at aspects of this, but we don't have a good picture. So anything we can do with a lot of instruments near even a moderate earthquake will go a long ways toward helping us see how real earthquakes work and if they're anything like earthquakes in the lab. A third topic that in Seattle we're very encouraged to see is this idea of the empirical Green's functions. We've known they work for a few years now, but just this year and last year it's been shown that they're effective around the basins. This is the slide that Eric showed from Denali, and this is from a GRL paper that's just come out for Tokyo, the equivalent study where, of course, with the tremendous instrumentation, they can take entire clusters of stations and with Green's function techniques, look at what the patterns of amplification across the basins in Tokyo are for earthquakes coming from different directions. And, of course, that's exactly what we'd like to know in downtown Seattle with our tall buildings that were built before we knew we had a subduction zone that had earthquakes. So I think this is extremely encouraging. And finally, we've heard this touched on a number of times, that if we have 1,000 instruments and we put them on a volcano, we'll see a huge range of things. And I'm always surprised how little we understand about the generation mechanisms of the different noises we see from volcanoes. So it's a perfect place for a 4D study, and we're doing a big study on St. Helens the next year or two as sort of a small pilot for what we might do with a large N study. So those are just 4 ideas that seem particularly exciting to me from the point of view of faulting and deformation. I think that's all I had. Yeah. Okay.
Eric, are you here? Yes, you are. Good.
I didn't get the marching orders, but I have a few thoughts I can share, but no slides, so it will be less than 5 minutes.
Well, what I'd like to do is actually open up everything for the planning forum. So can you hold your comment, or is it? It is really quick. Okay.
John, the seduced earthquake, please. Is that part of faulting and deformation?
Yeah, there are 5 topics that just want you to use.
Okay. Thanks.
Okay, thanks. I'm standing in for Beatrice, who I'm the last member of our committee standing, I think, here. Everybody had to go this morning. I just wanted to, I guess, pass along a few thoughts along the lines of what John just did in terms of what seems exciting in terms of the context of how this community and this community's science interests interact with the surface processes, both at short and at long timescales. And I think one of the most impressive things was the summary of the range of ways in which seismology and associated techniques in terms of noise and infrasound can be of use in terms of tracking cryospheric processes. I think we saw that in Rick's talk this morning. And in fact, to the degree that you're willing to share that talk, Rick, I think that would be really wonderful. It's a lovely review of what's out there at the moment. That seems to be a very well-established direction. I think what on the longer time scales, we didn't see as much here in terms of the linkage between the seismic images and then the geodynamics and up into the surface. And I think that, we know that I've heard a couple times say that both at the software level and the sort of infrastructure level, but also at the science, that it looks like some greater communication between this group and the geodynamics groups and then the surface processes groups above it. We too have that challenge of trying to really do interdisciplinary work is difficult. But there is some very exciting things on the horizon, I think, in particular in terms of looking at the influence of mantle flow all the way up to the surface and how that influences sort of the million-year evolution of basins and some of these systems. And there's I think, a fair bit of meat there for this community to think about going forward. I also think that there is a community of people out interested in what probably to you is very small scale or maybe even pedestrian questions about the geotechnical properties of the upper 10 meters of the Earth's surface, right? The fractured distributions set everything about the architecture of weathering, of surface area, global geochemical cycles, and the ecology, the biota that function off that landscape. This community, and particularly I think this effort to go into large N at small scales, big arrays, that you have a lot to offer in terms of helping the rest of us try to understand a predictive tool for what sets fracture distribution as a function of history and topography and climate and all those things. That's an incredibly important interdisciplinary problem, and those of us working on it from the other side are naive in many ways in terms of what is out there in capabilities. And so that's another direction I think that people can go. And I guess I would just close with the thought that, as an outsider to this community, you obviously are very proud of your organization, and it shows that this is sort of an exemplary organization in terms of how the effort to do community sharing, community data, open sharing, and facilities is really galvanized a remarkable sort of set of efforts that don't happen as easily in other communities. And so I'm very, impressed. And as you guys are, you should be suitably proud of that. So that's my thoughts.
So as frequently happens, unfortunately, in these kinds of workshop settings, all of our thermochemical people have departed for their flights to get back to the other side of the country. So one of the things that we'll be doing, and we'll talk about this at the end, is how we're going to pull together the information that the things we've been hearing in the context of this workshop and make it available for people who've been attending the workshop, but as well for people who couldn't attend the workshop. So we'll be posting information and down the road also requesting additional input from you. But before talking about next steps from the workshop, we want to open up for a broad forum to hear from you. And do people have some overarching burning things they want to say based on what you heard this morning or what you've heard over the last 2.5 days? We thought that might be the case, so we've prepared some slides. Oh, great, wonderful.
I got something. If you turn to the whole group here, one of the things IRIS has been really good at, obviously, is collecting and sharing data. But what's I notice it's a barrier to me, and I suspect it's an issue with others, is we also, these days, a lot of people have them and their grad students writing their own software to do lots of processing, and they're reinventing the same wheel, whether it's how the best way to do receiver functions or other types of processing. And we're not sharing that software. A lot of people kind of redoing the same thing in separate places. Is there interest and maybe capacity within IRIS to have some pretty basic things, ambient noise processing, receiver functions, other things that can be made available community-wide? They don't need to be, I guess, necessarily industry quality level, that we could start sharing with each other on a more regular basis, and IRIS provide the forum to do that. I was looking at IRIS's mailing list. There's nothing for that, a general mailing list for us to communicate with each other about software. That would be useful. So we don't reinvent wheels, right? And for me, being the lone wolf seismologist, one guy at an undergraduate institution, I don't have time or capacity to write my own software anyway. I'm quite happy to reference your papers, right, and use it to solve my local problems with the data I already have, or data I can get from IRIS. So that's something that's come up, and we've been talking off and on in different forums that's kind of come up in different.
Yeah, it's clearly been, I think, a message that's come across in a number of different venues over the course of the last couple of days. Yeah.
So that seems to me to be a great idea, and the reason I say that is because I direct the computational infrastructure for geodynamics, which has been doing that for the geodynamics community for a while. So we've learned a lot about how to do that, how to basically bring in software that was developed by individual, we call them hero codes. They're developed by the heroic graduate student working in an attic, and then when that graduate student graduates, it sits on the shelf. So we've been working for about 9 years now to pull together some of those codes and make them, bring them up to high standards, documented, tested, and so on, and then release them. So, we can share. You don't have to reinvent that wheel either of how to do that, is what I'm saying. We'd be happy to share our experience with that.
Great. Go ahead.
It seems to me that there are a lot of fundamental constraints that could be made if there were some very boring laboratory experiments done. And it's hard to motivate these through an individual proposal process. For instance, if I want to know if Brandon's tomography shows eclogite, I need to know the bulk modulus of omphacite. And no one wants to do that because it's boring. Or if I want to understand the mineralogy of the mantle, I have to make some Gibbs free energy measurements. And I wonder if there's a role for IRIS in motivating these needed studies that probably can't easily be funded as individual projects.
For those of you that don't know me, I'm Randy Keller. I'm the face of Oklahoma here. So you've heard a lot about Oklahoma, but not from me. So all I want to say is we're working very, very hard to run a good network. We're up to about 35 stations. I think perhaps half of them are broadband. We're getting the data online as fast as we can. We have good cooperation with industry and our regulatory groups. We're happy to work with you. We're happy if you come to Oklahoma and want to deploy, we can perhaps help in various ways with some sort of at least advice and connecting you with the right people and so forth. So we're an open shop, and I just want people to know we're working hard and we're happy to work with you.
I have a comment about hazards work, and there was a question raised yesterday about the appropriateness of IRIS getting into the hazards realm. And I know that there's been a sort of perception, real in parts, about there being sort of a sticky wicket between USGS in particular, which has mandates to do hazards work, and other groups who are interested in doing hazards. And I'm speaking partly as myself as opposed to an official USGS person. But hazards is a big word, and folks use it in ways that mean different things. But literally, all a hazard is what can happen. What characteristic of this particular thing, what are the characteristics of this particular thing? Fault, volcano, what are the range of things that can happen? And so anything that is involved in studying that is hazards-related research, and that is wide open. That's all kinds of scientific input, and there's no way that any single group can claim domain over that as an area of study. And so I would strongly encourage the IRIS community to continue thinking about that direction. Certainly on the volcano side of things, we don't have the resources by any stretch to constrain the hazards in terms of studying volcanic systems. What I would encourage is collaboration, so that when there are new results that people learn about particular volcanic systems, in our case, that there be integration with that knowledge. It's where the survey comes in is in applying that knowledge to the problem of when something happens, a response, or making some statements that have some sort of legal-ish type implications about, say, you can't build here because there's a lahar that's going to come through here. That kind of stuff is sometimes lumped into the broad hazards world. That's more hazard mitigation or risk. So I just wanted to sort of raise that point.
Yeah, no, thanks. I agree. That's a good clarification. And when people say, IRIS, should they get into hazards, it's actually, of course, individuals who do the work and do the research. IRIS as a consortium and as a facility operator helps enable and facilitate that. So there's certainly plenty of room for people to work on these basic physical processes and understanding, no question about it. Okay, so if there are no other comments right now, we want to try to maybe pull some of what we've heard into some kind of a framework that we can build on going forward. So I'm going to need the projector, which isn't showing the slide on my computer. Oh, that's so funny. It's not looking like that here.
Always does that.
Let's try this again. I had it the other way last time, so let's try this again. No, I don't need to see the notes. I'll try unmuting. Well, now we'll see. To mirror or not to mirror, that is the question. Oh, look at that. Either way. Yeah, that's not appearing on my screen.
Weird. Let's try doing it again.
Maybe bring John's computer up.
It worked. When we mirrored it, it worked fine.
Yeah, generally does. Try it again. And just hit the little guy. Yep.
Okay. Do you want to move over to here?
Sure.
Just bring thumb drive.
Let's try this one.
Yeah, we can try doing this real quick. Shouldn't be that difficult.
So to get you thinking while we're working on this, when Bob made his presentation, he
That's mute.
is this on?
It's muted from the back. No, it's muted from the back.
It's muted from the mic. Okay.
So when Bob gave his presentation earlier, he talked about having us think in terms of facilities or services or activities that are foundational versus frontier. And so maybe we can try to take some of what we've been talking about over the last 2.5 days in terms of capabilities that we have, capabilities that we don't have but need in order to accomplish the kinds of science that have been talked about here. And if we sort of look out 5-10 years, so not today, but out 5-10 years, what of the capabilities that have been discussed would we want to consider as foundational? Basically things that are part of our normal toolkit, tool bag that we can easily do, and what would fall more in the frontier area. And that's maybe a little difficult to think about, but so don't think about today and what is foundational or frontier, but look 5-10 years out, and what would we want to consider our core facilities, core services. Doesn't have to be facility in the traditional sense of the word, so you can think of it as services or activities that the consortium can be enabling.
And this was sort of what I put up yesterday, but we could talk about this and see if you have any input on this, if you think that there are additional items that should be part of the core facility capabilities. But why don't we just open that up for any comment or discussion? Yes. Okay.
We've heard on and off throughout the last couple of days how there's a segment of the political elite that is antagonistic towards our sciences. And I think outreach of some sort is going to be a fundamental process by which we can, if we're ever going to expand our field, we have to, there's so much public appeal to what we do. And if we can broaden our outreach in some way to really generate interest in what we're doing and political support, I think that would be wonderful.
Yeah, certainly one of the activities that is not on this list, but it was was mentioned because not a physical facility, but an activity is IRIS's Education and Public Outreach Program. So IRIS does have a program which one component of that is outreach, public outreach efforts to improve literacy on earth science and the value of earth science. So is that the kind of thing that you're referring to there, or are you thinking something different?
Well, I don't know. I mean, you may need.
I mean, I think that's essential, that component. But we may also need to think of a way, and maybe we can't do this with IRIS, but to organize politically as well.
Yeah, that's what I was wondering, if you were kind of more referring to sort of political advocacy. Yeah.
So let's keep in mind that this is fairly high-level bulleted list, and you might say, well, that looks like what we do today. So if it helps you, put some sub-bullets in there.
Certainly, I think within as I mentioned yesterday, I think within these 4 categories, there are a lot of questions that this community needs to address in terms of what kinds of capabilities do we think we are going to need in the 2020s for each of these 4 bullets. And those may be different. They may be very different in some cases from what the current capabilities are under those 4 bullets. And so I think one of the things, and certainly there's been a lot of discussions at this workshop about that, but one of the things that we need to do over the next year, let's say, is really try to flesh out what do we mean by, under these very high-level descriptions, what sort of more specific capabilities do we want to see in each of these 4 areas. Let's say if we accept that these are the 4 high-level core capabilities that we think we need. We're definitely going to need to be more specific about under each one what we think we need.
And don't worry about how we're going to get there. That's what we're going to have to figure out. But 5 to 10 years, since John is here, let's just say in 5 to 10 years, do we expect that a capability for the full wavefield imaging is simply, that's foundational. That is a core facility in that 5 to 10 year time frame. If we're going to actually do the science and make the advances that we've been hearing about, if that needs to be a core capability in that time frame, then we'll work with various people to figure out how we get there. But we really need to know these things.
Yeah, not surprisingly, that's something along the lines of what I was going to say. I think right now wavefields are a frontier, including at the very large scales at which we've already done it. And I think absolutely, to me, it should become core, and probably on the few-year scale. And it's going to fit exactly in all 4 of these categories. It's not just the full large numbers of stations, but also the large volumes of data and the computing resources that are going to be required to deal with those large volumes of data. So it really is ramping up what we're doing today, but ramping it up to a new scale.
It's essentially a very difficult question that you ask, because if you ask us to say what are the problems that we shall be attacking 10 years from now, we are not doing interesting science if we can predict that now. So, but there are some general rules, and that is whenever new fields open up, they give rise to new discoveries. And I think the one thing that I don't see here right now is an emphasis on the oceans, because that is definitely going to open up in the next 5 years.
But I think that could be one of the sub-bullets under
Sure.
Certainly the first 2 bullets here.
Yeah.
We could say we want both some permanent, when we talk about permanent high-quality broadband stations with real-time telemetry, that could include both land and seafloor stations, for example. So that's what I'm saying. There's a bunch of questions here that we need to sort of flesh out in terms of sort of a more detailed description of what capabilities we would want under each of these fairly high-level descriptions. I mean, another one just for the first bullet would be permanent networks of broadband stations in the polar regions, which we don't have right now. That would be another example of something that could be under that first bullet. And obviously under the second bullet could be, the mermaid concept that you described earlier today could be under the second bullet. So that's I think what we're saying is that we really need to, over the next months, not years, but months, we need to flesh out these very high-level descriptions of capabilities.
Or that our permanent stations, in fact, are environmental monitoring stations, not just broadband seismometers.
I think these capture a lot of the current capabilities of the IRIS, the facility, but I think an important aspect of it that might be more overarching is what about the capabilities of IRIS, the consortium? And I see each of these as something that you look at it and says, this is just a functional element that could be parsed off, operated by a technical services group or an operational paradigm like that. However, I think the strength in IRIS, as it's been developed and will continue into the future, is the adaptation of these capabilities and how we modify these capabilities to meet new scientific goals by the integration of all of this with the consortium input and the community guidance that allows us to be flexible and responsive within these facility capabilities. So I want to just make sure that
The sort of synergy between these different
that's right. How does the
activities.
consortium input drive the responsiveness of the facility capabilities on a kind of a real-time basis? And that's what we're doing.
This is maybe a very small sub-bullet. That's magnetocalorics. So IRIS has taken on a fairly central role in archiving and distributing data. Right now, the instruments are in the possession of Oregon State University. They're actually owned, some of them are owned by IRIS. And Adam Schultz may kill me for bringing this up, but nonetheless, I'm not sure whether that's, that facility being in the university is a long-term sustainable thing. I mean, it might be something that IRIS should be thinking about, is whether or not, they should take on that role of being an instrument facility for U.S. scientists in EM geophysics more broadly.
And I think the second bullet was specifically worded to not be just seismic instrumentation, but to be broader, to encompass things like MT or other instrumentation. Victor.
To get back to the point about education, and I think this also addresses Hoost's point, which is that one of the things that we know we'll need in the future is people, students who know how to use the tools that we have, and so teaching especially at a high level, so at a graduate education level, even at a higher level than that, when there's early career people who need to learn how to use certain resources. So say continuing the short courses that IRIS does, and maybe expanding that short course program to more things.
Great, thanks. Other comments? Do you want me to go to the frontier sign?
If people can expand their horizons even longer, yeah, sure.
It'll just be relatively. So these were based on discussions here, and one could add to this list potentially from the discussions over the past few days. But these were some examples of frontier facilities that we don't have now that we might like to have in the 2020s. And so, and we've heard a lot here about all three of these. So the Subduction Zone Observatory, the Seismic Wave Field Initiative, and Seismology in the Oceans. And I think all three of these areas, there seems to be, from this workshop, a lot of interest in pursuing that, and each of these three areas. And so sort of open this up for comment, and then maybe a little discussion of sort of how one might proceed in terms of this, because it's, I think, perhaps different approaches for each one of these and how one might move forward. So, but why don't we open it up for any comments or discussion? Ramon?
Yeah, I had a couple of thoughts here. One to add is the cryosphere. I think that Rick's talk was really spectacular, and it's quite compelling also just from a kind of key sort of part of the world we need to keep our eye on for lots of reasons, and it poses some interesting challenges technologically, but also has some really interesting phenomena. So that just one other thing that maybe isn't here. The Seismic Wave Field Initiative, to me, is really exciting, and I thought John taught me a few more things in his presentation today about that key frequency gap, which really maps into a key scale gap, which is really kind of the crustal scale structures, and then that means also it's really critical for both structure and source, and then also that even at finer scales for some of the surface process connections. So that is quite exciting, and just the way it's written here is sort of looks a little different than the other two, and then maybe relative to what John had written. So anyway, I'm enthusiastic for all of these, but had some greater clarity on the Wayfield initiative after this morning's presentations.
Mm-hmm.
Well, thanks for mentioning the cryosphere. I also wanted to know what people thought about keeping GABBA on this sort of frontier list, maybe by combining it meaningfully with large N more generically. I was going to refer to the bullet up there, but just curious.
Yeah, I was just going to type cryosphere in here, but...
okay. That's good.
So,
yeah. Certainly, these multi-scale sorts of arrays that Keith was talking about, a big component of that is the coherent recording of relevant wave fields, and certainly I think there's a lot of room to maybe have stronger initiatives by merging the two sort of at some level within IRIS in terms of its frontier facility strategy.
I mentioned in the breakout, the Subduction Zone Observatory, that the Ocean Observatories Initiative this next month is going to be lighting the cable, first light, and putting all the instruments on the seafloor. And it's definitely a multidisciplinary undertaking with biologists and physical oceanographers and geodesists and seismology, and we are collaborating with IRIS on making all the data from the seismic stations and some of the hydrophones available to the public through the usual approach to this. But I think this, coupled with the Neptune in Canada network, provides a real beginning, at least for the Cascadia Fault, to fill some of the extent of this thing from western, north, central, and South America to really begin this thing. There are efforts in South America that Dave mentioned. Chile are happening, but I think this doesn't require necessarily additional funds, but does demand coordination and collaboration to make this a success. So I think it may be a good way to start this new approach on the subduction zone.
Yeah, I think that's a great comment.
Maybe it's obvious, but several of these initiatives are, they're very compelling now, but they'll become even more compelling as, for example, in subduction zones, we see what happens after Japan in greater detail, and Chile and the places we've had the great earthquakes. These are things where we don't really know how exciting they'll be, but the existing studies that are coming out every week now make them more compelling. So we need to keep an eye on the very latest results for several of these initiatives.
Other comments or thoughts? So I think, one of the things that I think we'll be working on with you, the community, and partners is how we make initial steps on some of these things that are here on this frontier slide, so that down the road, things that are sort of frontierish actually are part of a foundational or core capability. And our sense is that there's probably different ways to begin to make progress on these initiatives now, even in a constrained funding environment. I think it's, we're going to have to find ways to innovate and continue to move forward. We can't stay still, or we really won't be doing the cutting edge science that we need to do. So I think, we've started on some of these. We have pilot projects that are going on, and these are and will continue to be some open data sets. So the more the community exercises these data sets and shows examples, these are things that we can build on. We might be able to use some of the additional funding mechanisms available, either through working with the NSF on MRI proposals, or potentially by partnerships we might be able to develop with industry where we can, move along the pathway on some of these things that are on the frontier list now, so that over even a shorter time frame in the next 2, 3, 4, 5 years, we're in a position to perhaps work with the NSF and have these kinds of opportunities part of SAGE and GAGE facilities as we move forward. So I'm going to have to refer to my notes here. So in terms of what we're going to be doing to wrap up the workshop, one of the things is we'll be working with the session organizers and the workshop organizers to actually produce a workshop report, and we will make that available for initial comments before finalizing it. We want to begin to build the documentation and sort of paper trail that's going to be necessary for the community to be providing input to the NSF as they consider how they want to develop a solicitation down the road. And again, we've heard from the NSF, both from Jim and Greg, that they're really interested in what are the science objectives and what facilities and services are going to be required. So we're going to be generating a workshop report, and that will be posted for comment, and then we will finalize it. There are a number of meetings coming up within the next year that I think also can frame some of this, and people have had slides up about those, the amphibious array workshop coming up in the fall that will address different aspects of this, and different people have talked about opportunities, white papers that exist and white papers that will be generated. We'll try to do a good job of serving as a central source of information so that people can figure out where there are opportunities for them to participate and provide input. I mean, the next 12 to 15 months is really that window for providing community input. One of the things that has been discussed between IRIS and UNAVCO and EarthScope and the NSF is a broad community meeting that will probably take place in the spring of 15, again, to revisit these issues and also provide this really important opportunity for community input to the NSF. So, the different groups will be working with the NSF to get a proposal in to fund that workshop. So sometime in the spring of 2015. So please watch for that. Please participate. It's going to be important. A couple people have mentioned that they miss the one-pagers, want opportunities for one-pagers. So I think one of the things that we'll be doing is actually making a round of solicitation for people to submit one-pagers. But I think these will be a little bit different than the one-pagers we've done in the past. We've done these one-pagers often when we've been in the process of preparing proposals for the NSF to show all the science we're doing. I think this time we want to see the science people are doing. These one-pagers are really great highlights, and actually people use them for all kinds of things. People miss them because they use them when they teach with their graduate students and for all kinds of reasons. I think this time we're going to want to know what you're doing right now, but there'll be an added bit like, what is it you want to do next, or what is it that you can't do now, but boy, if you could, you'd really make that science advance. So we're going to make a round of solicitations for one-pagers. We are going to be moving forward with the science committees. This is going to be an ongoing part of the IRIS governance structure, and it's one of our ways that we are trying to bridge to other disciplines. And so these are going to be committees that involve not just seismologists, but other earth scientists as well. We're just beginning the process of pulling these committees together. So on the first day, you saw our co-chairs and our board liaisons. These committees report directly to the board. We're going to be populating those committees. So there's lots of opportunities, and we're interested in people with diverse perspectives, diverse backgrounds, and different stages of your careers. A couple people have come up to me and say, hey, I want to be involved. I've got your names, but don't be shy. If you're interested in participating on these science committees, please let us know. Talk to the co-chairs, and we'll be building out that membership, and we'll be engaging those committees, well, forever, but your term wouldn't be forever. But for certainly in the next 12 to 15 months, these committees are going to be important, play a very important role, for IRIS as we really sort of define the overarching science goals and the contributions that seismology can make. But also one of the things that I think I've heard throughout the meeting is the need to bridge to other disciplines and find ways for us to do that better, more efficiently, more effectively, and regularly. So we want to build that into the way we operate. And these committees will be a first step in beginning to do that, certainly not the only way of doing that. So we will be moving forward and populating those committees. So I think we've got a lot of input during this workshop. We'll be pulling it together in some sort of an organized format in terms of our workshop report. And again, I think over the next 12 to 15 months, there's going to be a variety of ways that we'll be seeking your input, not just through workshops. So, please, when you receive a request for information from us, do respond, because these next 12 to 15 months are really just that sweet spot, and we really want the community input. So with that, I really want to thank the organizers of the workshop. It's a lot of work to do one of these, and so I want to thank the workshop organizers. I want to thank all the session organizers and session chairs, because I do know how much work it is, all the speakers, and all of you as participants. So thank you very much. Thanks.